Hello, my wonderful students. Let's learn about some equipment you need for the labs this year, as well as learning about kinematics. So here is a LabQuest. It's adorable. It's like an interactive computer for equipment. There's a power button at the top left. If you flip it around, not on that side, but there's holes for some equipment that we're not going to be using much of. There's a stylus right there. So you can see how the screen rotates. It's normal. You'll be playing around with this. Here's a motion detector. Pretty cool. It has an adjustable head. It's made of gold. Gold foil, I should say. And what this does, it spits out high-frequency sound waves you can't actually hear. You can just hear the clicking part of it, but you can't actually hear them moving. When something's in that cone, it hits and goes back. So we have a LabQuest app. That's what we care about. We can use our finger or touch it. There's the connection for the motion detector. We're going to use the top because that's where it fits. In Sonic 1, you get the power button. Open the flap, push it in, make sure it clicks. You should hear a little sound coming from the LabQuest. Now, the motion detector is unique. It can detect from 3 feet to like 24 feet away. You're going to see what happens when you get too close or when you get too far. So what we're going to do is we go to the LabQuest. You can see now it's reading 2.258 meters. That's how far the ceiling is as it's pointed up. Let's go to the little graphs. There should be two if you do this right. Position and velocity. So I'm going to turn the button on the bottom left. That's going to start recording for like about a couple seconds. You hear clicking sounds when you do this. It's reading 2.5 the ceiling until I put my hand in front of it. When my hand's in front, it drops down to almost 0. When I move my hand away, it reads the ceiling again. Now, if I put my hand really close, you can see it spikes up to around 8 meters. My hand isn't actually 8 meters away. It just simply confuses it. So you got to be careful exactly how far we are and constantly looking at it. And now it's time for the ideas we're going to be kind of testing with this lab equipment, and that's kinematic relationships. So you're about to make a big table with me to express all the major ideas we've learned so far, both symbols, ideas, and units. So the first thing we're going to talk about is the symbols, the ideas, and units. Let's talk about position. X or XF is what the position is at the end of some time period. Measured in meters, it can be positive or negative, and it's completely arbitrary. You can put any number you want for that point. You can pick any 0 values you're starting. The same is true with X naught, which is the starting position at the beginning of the same time period. So for example, if you walk from my room to Skeel's room, you can call my room a position of 0, Skeel's room a position of 40 feet, or mine 60 feet and Skeel's 100 feet, or vice versa, whatever. What matters is the change in position, which is delta X. And we call that displacement. And remember, change is final minus initial. And it's measured in meters, which is positive and negative, and it's not arbitrary, because no matter how you set your beginning and end points, it's always at the same distance between them. V and VF is the velocity at the end of that same time period. And it's instantaneous, which means it's the velocity just at that moment where the time ends. The moment before, if it's accelerating, it could be different. V naught is the starting velocity, the velocity at the beginning of some time period. And I just noticed that the X naught just says starting position at the beginning of some time. My bad. The phrase drop, for example, means the velocity is 0 from the air. Stop is the velocity of 0. Rest is the velocity of 0 as well. Not overall, just simply at some instant, usually the initial or final points. And remember, final and initial, you can actually make them any points you want of some time period. Time is arbitrary, so the initial and final points are arbitrary. Then we have time, like I said. Time is not a single value. Time is always a time period. It's a difference between two times. We're measured in seconds. V with a line is the average velocity, the overall displacement of the overall time. It's not really that useful because, again, if you're accelerating, the overall and the instantaneous are much different. And that's why we finally end up with the idea of acceleration. And acceleration is how much your velocity changes every second. As you can see, when in a situation, we can define this beginning and end points in time, whatever we want. As you can see, as long as it works out, we're good. When something's in the air, if it's undergoing gravity, acceleration is -10, and a constant velocity means although the numbers may not be changing, you could still have an acceleration, because if you're going in a circle, there's an acceleration there because you're changing direction. On the AP formula sheet, there are 3 equations that relate these. You will always have these equations available. The first one, Vx equals Vx naught plus Axt. The x just means you're going in a straight line. You can't have, for example, a right velocity and an up velocity combining. The next one, x equals x naught plus Vx naught t plus 1 half at squared. Again, you can't have an acceleration upward and a velocity to the right and use that mathematically. Last, Vx squared equals Vx naught squared plus 2a x minus x naught. These are our 3 relationships. We're about to do 2 problems and show how they work. So let's take this little paper and move it to the side. And let's write our first one, of course, about a panda. As you're going to see, it's not the math that's difficult. It's understanding what's going on and, more importantly, picking the correct times, using the correct knowledge, and figuring out what's exactly happening. We're going to turn these ideas into words and situations. We're going to have to be predicting what happens if you double the acceleration. How is the thing moving, blah, blah, blah. But we got to start with the basic math before we go into that complex stuff. A panda starts moving away, and after 2 seconds is going 4 meters per second. Then accelerates for 6 seconds, covering in 40 meters. What's his acceleration? What's his velocity after the 6 seconds? I highly recommend making a little table of what you know. We're going to call it the variable and value table. So the variables, 2 seconds, 6 seconds. Well, my time is to be from 2 to 6 seconds, which is a 4-second difference. The initial velocity is the velocity at 2 seconds, which you know is 4 meters per second. The 40 meters is how far we go from 2 to 6 seconds. That's your delta x, otherwise known as displacement. I'm trying to find acceleration. I'll write down goal there. So we have change in position, acceleration, velocity, time. That looks like the black one because you have x and x final. So let's write out the equation. X equals x naught plus v naught t plus 1/2 AD squared. Don't have to worry the x's because they're all on the same line. I'm going to move the x naught over because x minus x naught is displacement, and that's 40 meters. V naught is 4, time is 4, plus 1/2 times a times 4 squared. All right, so 40 equals 16 plus 1/2 times 16, which is 8. If you do the math, you get acceleration is 3 meters per second squared. I can put that in for my goal now because that's good. I'm making them all positive because it's completely arbitrary. Now let's use logic for the velocity. We have 4 seconds of time, and acceleration is positive 3. So we gain 3 every second for a total of 12 meters per second gained. And since it started at 4, 4 plus 12 is 16. Using an equation just to make sure of it, I could plug in the numbers. And I get, that's what I had before, 16. Right on, I rock. Now for a more difficult one. Again, not in terms of math, but in terms of ideas. So look at this car. It's going positive 20 meters per second. And it deaccelerates, even though that word is horrible, so I put in quotation marks, because deacceleration is just acceleration of another name, at a rate of negative 0.5 meters per second squared. If it was going backwards, that deacceleration would be accelerating it. How long to stop and how far did it travel in the 2nd to 5th second? Ooh. Let's do the how long to stop. Let's use logic. It changes by negative 0.5 meters per second. So after 1 second, it's changed by negative 1. So I'm going to guess it takes around 40 seconds because you're going from 20 to 0, and you lose 0.5 every time. So using math, I'm going to figure out the initial velocity is 20, the acceleration is negative 0.5, final velocity is 0. I chose the correct equation. And lo and behold, I got 40, so it works out. Now, 2nd to 5th second means most people say the time is 3, but there's a big thing you have to ignore. Let's draw a number line to make this point happen. 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. We know it's slowing down, so the gap between numbers is not going to be the same distance. If the initial velocity is 20 and time equals 3, well, there's initial velocity is 20 right there, and time equals 3 means we're going to find the displacement from 0 to 3 seconds. But that is not the same as from the 2nd to 5th second. That's the t equals 3 we want, but the initial velocity there is not 20. So we got to find the initial velocity at 2 seconds. And using logic again, we have to do it. Now I say simply, if you're going at 20, let's write down what we have. The time is 3 seconds. The initial velocity is what it is at 2 seconds in. Well, after 1 second, we lost 0.5. Another one, we lost another 0.5, so it's going to be 19. The acceleration is still negative 0.5. It's a constant. We're trying to find the position. I'm sorry, trying to find the displacement. I can pick an equation now that I shifted my ideas. So the whole point of this, again, as you see me do the math, is that even though there's a 3-second gap, if you just plug in time is 3 and v naught is 20, you're going from 0 to 3 seconds, not from 2 to 5. So you have to constantly look at what your time period is and figure out what is the initial velocity for that time period. And it's something we have to learn and apply constantly. As you see me do the math right here, I'm just kind of doing it low and slow. Fractions suck. We can actually get a value for end. But at this point, I'm like, you know what? Let's just do it. Negative 2.25. And you get 54.75 positive as my displacement.